Okay, welcome back to my Programming in Assembly video series. In this series, we're just trying to create a little number generator game. So let's go ahead and jump back into the code. I have to fix this every time. Okay, so in the last video, we got to the point where everything was basically the program's done, except for the fact that we don't have any way to, we don't currently have anything that's generating a random number. So every time we play the game, we are relying on a fixed number, a hard-coded number. But before I get into deciding exactly what method to use to generate that random number, I kind of want to clean up some things before, because if I move on to the random number generator, I might never get back to this other thing I want to do. And what it is that I want to do is every place that we are presenting information out to the screen, we have to manually count up these characters and then type that in, and that's just not very good. And then you'll notice too that every time we present information, we're doing the same four things, the same five things. We're loading standard out into register 0. We're loading the memory address of our message into register 1. We're counting the characters and manually typing that in. We're setting register 7 to the right value, and then we're doing a service call. So, and we're doing this at least 4 or 5 times in this program, and we could potentially do more. So that sounds to me like something that needs to be a function called a subroutine. So I'm actually going to make it an external file so that, because I have some other ideas for some little programs I'd like to write. So if I make it like a little external file, then I can just reuse that almost like a library or something. So let's do that. Let me take this bit here and just copy it into memory, and then let's quit out, and let's create a new file called bad at coming up with names. Essentially, it's like a little print routine. So let's just call it print_s. It's probably not the greatest name. And let me just go ahead and paste in that stuff for now. And so for this external file, we are going to have a global directive at the top. And it's not going to be called start because we're going to be linking this program. We're going to be linking this file into our other one, and we can't have both of them called start. So I'm just going to name this one after the, what it is that we're trying to do here. So let's call this, let me just think about this for a second. Let's just call it begin, actually, because we just want to jump to the part of the code where we're going to begin. So let's go with that, and then this will be the label that it jumps to, except it's the other way around, like that. Now we have to make some assumptions when we use this, and let's put those assumptions, let's spell those out at the top of the program. So the assumption is going to be R1, register 1, will be preloaded with the string before we ever call this, and that's a reasonable assumption to make. So let's actually not say will, but let's say must be preloaded with the string to be printed before this function is called. So that means that by the time we get into here, we don't need to do this step because it will have already been done. The rest of these can be, the rest of these we will take care of inside of this program. Now, one thing I'm not sure of, when we link, do I need to redeclare standard out and all this stuff? I'm actually not sure. Figure that out later. Now we're gonna need to count this. So let's see. So we're gonna need a loop here, and we're gonna loop through each character in string R1. So we're gonna do the LD load register byte. We're gonna load 1 byte at a time, and we're gonna load that byte into, let's just say, register 3, and we're going to load it from register 1, because again we're making the assumption that register 1 has been preloaded with that string, and we're going to load 1 byte. And we are also going to make an assumption: the string that is loaded into R1 must be of type ASCII's, not .ASCII. This ensures the string will have a null byte at the end. So essentially, that way when we're going through the characters, that way we know when we're at the end, because we can't, some of the strings aren't going to have a new line, so we can't rely on the new line. For example, our prompt doesn't have a new line, and each string is going to have a different way of ending. So the only way that we can guarantee that all the strings end the same way is if we require the strings, either the user will have to append ASCII, or we'll have to append a null byte onto the end of each string, or we will say they must have used ASCII's. A third option would be that they could use the ASCII string, and then we will append the null byte onto the end of it as the first thing we do. But the easiest thing to do is just to change all of our string types to the Z type ASCII's. Okay, so after we load the byte, we want to see if that byte is the null byte. So we're going to run a compare, and we want to say, is the byte that we just loaded in R3 a null byte? Is it equal to 0? If it is equal to 0, then branch. Yeah, we're done. So branch out of here, branch to, I don't want to say exit, because that, again, I don't know if labels can be used. I don't know if you can use the same label when you're linking programs together. So for now, let's just say branch to finish, or done. Actually, you know what? I'm going to see if we can just, because I prefer to use it like this. Although, honestly, it's not, we're not exiting anything, we're just done. So branch to, you know, job's done or something like that. Yeah, branch to finished. Oops, wrong way. And then we'll have the end directive at the end, just so we know when we're done. Okay, so let's think about this. And the other thing is, we are messing with registers here, so as soon as we come in here, we should probably preserve the state of the registers, because if we want this to be general purpose, we don't want to stomp all over other stuff that people may have in their registers. So as soon as we come in here, let's push onto the stack all the registers that we're going to touch, which is going to be R0, R2, R3, R7. And then we should also push onto the stack the link register. That way if this gets if this gets called in a nested situation, we can unwind. And then right before, so when we're finished, we need to pop off of the stack everything, R0, R2, R3, R7, and the link register. And then we need to branch exchange back to the link register. That's a safe way to do this because, again, you don't have to push these things onto the stack, push them onto the stack and pop them off the stack when you're only, like, basically when you're only going one level deep in your function calls. But since we're kind of wanting this to be general purpose, this could potentially end up getting called 2-3 levels deep, in which case when we return back to the link register, we want to make sure that we're going back to the one that called us, not whichever link register happened to be last. Anyway, so we begin, we push those onto the stack, we pop them off the stack as the last thing, and then we're going to load register 3 with 1 byte from register 1. Then we're going to compare that to 0 if it's equal, then we jump to finished, and if it's not equal, we keep on processing. Now this only needs to be done one time, and this only needs to be done one time, and this only needs to be done one time, so we can actually probably just put that down there. Like right as we finish up, we can make the service call and then pop registers off the stack and work our way back. And then this value will eventually be populated with our total, our count. Okay, so I need to keep track of what our count is. So let's say that register 2, we're going to initialize that to the immediate value of 0. And then every time we grab a byte off the string that's not the null byte, we'll increase the count of register 2 by 1. So as soon as we get past this point, we will add R2 to the immediate value 1. So this is like saying R2 equals R2 plus 1, or in C you could do it like this, plus equals 1. Or we could also type it like this, which is literally saying R2 equals R2 plus 1. Whichever way, but a shortcut is kind of just like that. Okay. So we don't need this, obviously. So once we add the number, once we increment R2, we need to loop back around unconditionally. There's nothing to check. So branch to I'm gonna see if I can I don't know how the scoping thing works. We'll see if we can reuse certain labels like this loop. And I guess what I should probably do is maybe make it like that. That way it's clear that this loop belongs kind of to this routine, and this, you know, kind of like using tabs to nest things. Is that all we have to do? And I guess what I can do also is I can just move these things down here. That way it's a bit... So basically right before we make the service call, we're going to load register 0 with standard out and register 7 with write. All right, let me think through this. So we push these onto the stack to preserve their values. We initialize register 2 to 0 because that's going to keep track of our count. And the reason that we're using register 2 to keep track of our count is because that's the register that's required by this system call reference. We could use any register we want to keep track of the count, but it just makes sense to use this register since that's the one that needs to contain the size anyway. Because otherwise we would just end up having to copy whatever register we were using into register 2. Okay, so let's give this a test because I think it's right. All right, so let's modify our makefile, and we're gonna take this, we're gonna copy it, and we're gonna change this to print, change this to print, and we need to add print.o onto our link so that they get linked together. And now we're gonna run this and see how many mistakes we made. Tons. Okay, so that answers one question. So standard out and write did not, it's not aware of those, even though they're defined in main. So we will go ahead and define those here. So dot equal, or dot EQU standard out is 1 and write is 4. Okay. And just in case that gets confusing later, let's make sure we put that text section there. Let me actually do it this way. Put that there. Those can go there. And then if I need a data section, I can put it right there. All right, let's try this again. Print O. Do I have to have this on here? Not sure, actually. I'm not very good with makefiles. Ugh. I think... You know what, let me quit out of here. Let me make clean. What? I'm just going to do this by hand. I'll figure out the makefile later. So assemble -G, and we're assembling the print.s file, and the output is going to be print.o. Okay, so there's a problem in the file. Okay. Line 28. Oh, I didn't declare that. Or I didn't define it. Got it. Okay, now let's try this. Okay, so now on the makefile, so the makefile was fine. Okay, so it's building, but is it working? So what did we call our function? So I don't want to call our function begin. I want to call it print, so let me just rename that to print. And it looks like having loop in the print file is fine. Okay, now let's edit our main file. And let's just try one of these really quick. So we will comment out that, and that. So to use the function, it requires that we've already preloaded the string into register 1. And now we want to print, or rather we want to branch and link to print. Let's see if that works. Nope. Okay, well, it's over 20 minutes for this video, so I'm not gonna work on this at all until we come back. But I'll go ahead and end this video here and then pick this back up in the next part. Thank you for watching, and I'll see you in the next video.